if you've been around the data streaming community, you might know me from Apache Flink. I was one of the co-founders of that project, and Restate is very much related. I don't think we're seeing the slides on screen right now. Maybe we can get them on the screen. Thank you. And yeah, Restate is in many ways related to the Apache Flink journey, if you wish. So probably for the last, I don't know, 10 years, whenever I started a talk in this space, I probably start with a slide like this to just like put a little bit onto the map what we're doing. So event-driven applications, if you talk about event-driven apps, there's a whole spectrum. It's not one thing that people refer to. There's a whole spectrum from the more analytical side to the more transactional side. Analytical being, aggregations, joins, and so on. Transactional being, you take an event, you might run it through some complex control flow, talk to 3 other APIs, eventually update a database, and emit some, downstream events or so. The analytical stuff is often okay-ish with like near real-time, couple of seconds latency. Often transactional is like more in the critical path, is even more latency sensitive. Interestingly, if you look at what has been developed over the past years, a lot of the projects that came out of the ecosystem of all companies focus on the analytical side, and I think that's because this is it's both a very valuable problem, like gaining insights into your data fast, but it's also a very well-defined problem. Like folks are usually doing somewhat similar operations, like joins, aggregations. There's like standards, like SQL, redefinition of SQL to like incremental view maintenance and so on. Like this is very well defined. Like it makes sense to build good tools there. On this side of the spectrum, there's not too much happening there. I feel like this is still very hard. Like there's no such thing as the equivalent of stream processing on that side of the spectrum, and I think that makes it often surprisingly hard to actually deal with those things, because what actually happens is you're down to to building sort of manually with the Kafka consumer, manually with updating state and this and that. But there's a lot of like valuable stuff happening on that side. Like the analytics often compute like the background sort of knowledge data and so on, but very often, like the actions that actually like book the revenue, generate the value, they're often on the transactional side of things, right? They very often take input from the analytical side, but this is where a lot of valuable stuff happens, and it's actually surprising that so little stuff has happened there. So if we look at the spectrum a little more simplified, analytics, like the OLAP of event-driven applications, lots of good frameworks. The OLTP side, not so much. Like roll your own, and it's surprisingly hard to do this as I will argue in a moment. And in this talk, so our proposition is durable execution is actually an amazing model for the more transactional side of event-driven applications, and particularly if you take sort of an approach like Restate does it for durable executions, kind of marrying durable executions and event-driven concepts. So that can actually help do a lot of like almost magic stuff on that side, and kind of give you the same benefits as stream processing gave you on the analytical side. On the analytical side, if you use stream processing, you're not worrying about like state consistency and failover and everything. Just like it sorts itself out, it's correct. On the transactional side, you write your retry loops, and you have to do your locks and transactions and all of this. Like, and it's corner case after corner case after corner case that you discover over time. And I think durable execution can give you something close to the like magic of stream processing for this side of the spectrum. So let's start with some code that looks like a super harmless example. It's like a 3-4 line function, and it's something that you look at and like, I should be done with this in half an hour. But then then the usual stuff happens. So let's take this piece of code. It's a function that calls 2 APIs to create a new user and then apply a set of permissions to that user. And let's just, for the sake of this example, assume there's like a different API for the user and for the authentication. And we're really interested in getting sort of a correct result out of this. Maybe it's not too bad if we call, create user twice and we have like an empty user there and then a complete user there. But what we really don't want is like in the end 2 users being there with like a partial set of permissions. Or actually we're creating a separate user with a full set of permissions and so on. Like, it's not where we want to end up. So how do we make this reliable, and why are even simple things like this like quickly rabbit holing in complexity? Like as a mental model, you can think of this as it's kind of like a 2-step workflow almost. You're doing one step and then you're using the result of this in another step. So and therein lies almost the source of all the complexity. So let's say we want to make this reliable, and we're in the Kafka Summit. So the first thing we do is we're saying, okay, if this fails in the middle, we want to make sure this is like reliably retried. So we're actually not triggering this in a transient RPC call way, but we're putting a queue in front of it, Kafka or so. Okay, that's good. So the event comes, stuff executes. If it fails in the middle, the consumer group will eventually make sure that something else is assigned, will redeliver it. So far, so good. But now if we crash somewhere in the second step, we're actually creating a second user and applying a second set of permissions to the user. It's not quite what we want. So maybe you can say, okay, yeah, look, let me create this thing, actually store it in a database. So that whenever we start with assigning the permissions, we know we're referring to the same user. If we crash, we look actually up in the database, did we create the user before or not, and we try to stitch it together. But this thing actually requires a lot of other plumbing around as well, because now we actually have to figure out what do we scope this to? Can we make a differentiation between what is actually an invocation, what is a retry? How do we make sure that we understand another invocation it's not the first one, it's maybe, it has a relationship to previous execution attempts. So we probably need something like request IDs that we most likely would actually have to push upstream, like before the queue even, so it's actually stable when it goes downstream. And that looks like maybe it works, but then there's this nasty thing in these distributed systems that happens that this thing might actually fail, and the consumer group might rebalance and start a new thing, but it turns out it didn't actually fail at all. It was just a little slow, I don't know. Be that a garbage collection, be that like a Docker container migration, or it just be that, somebody was reconfiguring the overlay network, and for some point in time, the Kafka consumer and, the Kafka broker and the consumer couldn't communicate and, timed out. But the process is actually still around. So this kind of zombie process or split brain situation is something that's like one of the nastiest things to happen. And if you really want to get rid of this, then it gets actually quite tricky. You have to come up with a versioning, maybe monotonous versioning scheme, or in the general case, you might actually even have to pull in something like Zookeeper for distributed locks. And we're already at the point where, this should have been a simple thing, but if we want to make it really robust, it's actually there's this really a rabbit hole of things we need to worry about. So, okay, that doesn't look like really we want to do it that way. So sort of the motivation for durable execution is a bit like, could it actually be as simple as that? Could it be something where we say, these are steps where we care about them running and their result to be persistent, scoped to an invocation, to a retry, so that, if we go to a second step, we can refer to a stable previous result, and, these things kind of sort themselves out. And that's actually what you can. This is code from Restate. In other durable execution systems, it might look a bit different, but conceptually, it's the same thing. You basically just register your operations, the way you care about them being persistent and reliable, and their results being recoverable, just as lambdas to a context, and then everything just happens. And what is actually happening there in the background? Just to go through a simple example. This is not Java anymore. It's TypeScript because it kind of fits better on a slide. But bear with me for a second here. Okay, so the core idea of durable execution is you're running a journaling process. As you're going through the code and you run an operation, you actually remember that you ran it. If there's something that's not a void return type, you actually capture the return type and put it in a journal. Think of it as a super fast write-ahead log that just runs in the background. So what that gives you is, if things go up in flame, you can basically just say, okay, I'm starting from the beginning, I'm running this, and for all operations, every time I have such a context.run thing, I'm going to look in the journal. Did I find this before? If yes, I'm just going to restore it from the journal. If not, then I'm going to execute it and also append it to the journal. So it's kind of like a lightweight write-ahead and replay log that just runs as part of the execution. So far, so good. That sounds like maybe a useful piece, and it also sounds like something you might, just build in a few afternoons as a library that just stores these things in a database. But that's really only half of the problem. And if you go back to the previous slide, right, that maybe is the problem of writing something to a database. Now, you still have the problem of correlating it to invocations, understanding how to map this to retries. You still have the problem of fencing off like zombies and concurrent invocations. So this really only works well if actually the journaling is done by the same process that actually manages the invocation. So you have something like a process that takes the original function call, becomes sort of a mediator, a middleman for the function call, invokes the function, records the journals somewhere, the journal entry somewhere in its storage, and then if something blows up again, that system that did the original invocation does a retry invocation, understands what parts of the journal to attach to the retry, and continue. So if you do this, then you can actually get sort of some almost, out of the box consistency. And if you take a step back, why does that actually work, and why does it work so beautifully out of the box? It's because we're doing something where we're avoiding a lot of distributed coordination. Namely, we're putting the same component in charge of persisting invocations, the fact that we want to call the function, the retries, the recording of the progress of the partial results, combining the retries with the exact partial results that have been observed, and locking, fencing off previous ones. These are all things that we manually did when we built this ourselves, and we all did this with different systems. Fencing we did with the Zookeeper, like recording we did with the database, like combining the retries we did with like the versioning and the request identifier in the database together with our request identifier and the queue and so on. And we had just 4 places or so where we had pieces of the ground truth, and the complexity was like we have to stitch it together to actually figure out how to really restore the system to a consistent place. What we have here is we just put the same component in charge of all things. That component has the one ground truth on everything, and can just make it work. So it's basically just saying, put the distributed coordination away from the application process. So one question, when we started working on this, right, we come from a stream processing background, and I guess, Kafka Summit has probably a big stream processing background. So one of the first things when we're looking at this problem is like, can we actually just do it with stream processing? Can we just build it on something like Flink, Kafka Streams, or whatever? Let's say all operational and latency concerns aside, like is stream processing actually the right model for this? And it turns out like for a bunch of things it is, because you could theoretically just say do each step in like a stream transformation, write it to a Kafka topic, stream transformation, Kafka topic, and so on. There's just a few things where this isn't great, and that is, if you do actually want to do this, you have to know what your control flow is up front. You have to know all the paths that the events, like you would kind of have to, stream processing needs to know the DAG up front. And sometimes you don't know this. If you have like loops and complex conditions, you either have to really build a flow of all possible paths or somehow multiplex them into topics or so. It just, at some point in time, doesn't quite become possible anymore. If you do it this way, you have the nice beauty of being able to just basically use all your programming language control flow constructs, branches, loops, exceptions, and so on, just as they are, and it just keeps on working. This thing actually, this is a nice version of the Sagas pattern. We're going through a set of products that we want to reserve. If we see a terminal exception, for some reason, just couldn't reserve that one, might be, because it was out of stock, might be because the service just gave up on us. Then we just go through whichever reservations we collected before and undo them. And wherever it fails, it doesn't actually matter. The replay from the journal will sort of make it appear as if it picked up where it left off. And it will like drive it forward from there, even if forward means like actually going back and undoing the previous work. So this is something that actually works pretty well in a durable execution framework. The other really beautiful thing is, in my mind, observability. So if you've ever built like a big streaming applications and you put in an event in the beginning and for some reason not the right result came out of the end, I don't know, let's assume we do the permissions thing in a streaming workflow. We're creating a user, but then for some reason, the user doesn't have the permissions we want, and now we're stuck looking, okay, like this stream transformation did something, and this did something, and like where's our intermediate state? And we have to search through all the Kafka topics, so to find out like where things are stuck. The fact that everything is still together in one invocation and like in a write-ahead lock within this one function call actually basically lets us just inspect that one write-ahead lock for that function call and basically tell us, where are we? And I'm not sure if the resolution or the size of the picture is big enough, but this is like from the Restate CLI. If we just query where is something, it would just tell us, okay, hey, those and those and those things are steps I've already executed. There's some condition I'm waiting on, but I've also made like a bunch of like calls to other services, executed a bunch of steps and so on. It's just beautiful observability out of the box. Also, let's just look at one slightly more complicated example to maybe show you what you can do with this paradigm. I guess you all know this case. You're signing up for a new service with your email, and they want to verify that it's really your email address, so they're sending you an email with a link that contains like a secret, and then you click it, and then they check it against the secret they stored internally. I don't know if that's the best way to implement it, but that's kind of when I sat down and thought, okay, how would I implement this with some services and Kafka and so on? How would I do this? And it's a bunch of processes, some queues in the middle. There's probably some intermediate state, a store in various steps of the different processes in a database. And then I didn't go to thinking about timeouts, cancellation, deduplication, concurrency, and so on, because that would actually have really blown up this example and not make it fit on one slide. But it's a bunch of things, even on the happy path. And then, if we want to actually deal with the unhappy paths, it's not a weekend project anymore. So what if it could look just like this? Again, I forgot to update this to Java. This is Python now, but bear with me. I hope this is readable. So assume you can do something just like that. You're defining basically two functions. One is the function you call when you create the user. The other one is maybe the one you wire up to to the link that the user clicks. And that's really all you do, and it just works, because there's a bunch of things that just happen here in the background when this code runs. Like number one, all these functions have, again, this like durable execution workflow semantics. So we don't actually need to store the secret in a database or so. The secret is just in the log, in the write-ahead log. It's a local variable, and it's persisted in the write-ahead log, so we can recover it after failure. We're sending the email with the link. We're attaching the workflow ID in here, which is like the sort of the logical identity everything is scoped to for this request. We're doing this also in a context of run lambda, so we don't send the email twice if we crash later and then recover. And then we're doing something like we're creating a durable promise. I mean, in Java terms, think of it as a completable future or so, or just a future. We're creating a promise, email.clicked, and awaiting that value. And then we're completing this from another handler. And if this actually is an application that scales out, and it turns out that this invocation actually runs on this process first, then it crashed and then recovered there. And then the resolution, the click, actually runs like routes to a completely different process. Also doesn't matter. It feels like you're using a future in your programming language. It's actually a durable future that's in the durable execution runtime. And so it just wires up across failures, across process boundaries and everything. And in a way, if you think, it's like a bit of a stream processing type of join, but it's a very natural way to model this and as a programming language construct. There's also a nice feature some of these languages give you, if the handler is durable, you can actually suspend it, like throw an artificial failure at any point in time. If you're waiting on that future, why keep the thread alive, right? I mean, the user might click on the link tomorrow or so. Like, you don't want this running for a day. Just make it go away, and when the future is complete, let the system recover it, replay it back to that place, and then continue. So having durability also allows you to just stop, shove resources away if you don't need it. You can actually put this on something like AWS Lambda, and it would just go away instead of keeping the Lambda up and waiting and make you wait for the pay for the wait, sorry. All right, so there's a whole lot of things that one typically encounters when building these types of applications that these systems help with. I've talked a lot about durable execution, restate. Let me just give you a brief intro to the specifics of restate. Durable execution is a bit of a broader context. There are various systems implementing flavors of that. It's they're not all the same. I think restate has a particularly interesting flavor. A lot of what I showed you here is in the restate specific flavor. Some of that generalizes, some of that not. There's no smallest established common denominator in that space yet. It's too much of a, I would say, nascent growing niche at this point. But let me just tell you a little bit about restate. So I guess the basic premise of why we're building it is it exists so this is not where you end up being. You're trying to solve a problem and you're doing it the way Amazon recommends it, by pulling in 150 different small individual services and stitching them together. Restate is, you can probably say it's event-driven applications done right or done simple. I think the long form is it's a fast transactional, stateful, serverless, durable execution engine for event-driven applications, but that's maybe too much, so let's actually stick with that. conceptually, how you can think about it is the following way. It sits in a somewhat similar place as message brokers or queues like Kafka. The way you integrate it with your services is you're writing services look like RPC services. They're just handlers, and then you're putting Restate as a proxy in front of that. And Restate being the proxy means, instead of invoking the service directly, you actually call Restate. Restate sort of proxies it to the service, maintains a lifeline to the service that deals with all these aspects of like journaling, fencing, state management, all those things that you otherwise have to manually do. So one way to think about it is it turns ephemeral invocations into like durable stateful invocations by being a proxy in front of the invocations. And the core idea is let's uplift our abstraction a little bit. If you're building a distributed system or like microservice infrastructure, you have a lot of like interesting tools available: queues, distributed logs, key value stores, timers, workflow engines, and so on. The hard part is not that these systems aren't good. Like there's lots of absolutely great variants of this. The hard part is you have to kind of coordinate across them in your application logic. This is where a lot of the brittleness is. So can we just say, instead of thinking in queues and distributed logs and so on, let's think in durable handlers, durable promises, durable objects. That would allow us to get a lot of problems out of the way. And maybe just to make it concrete, this is Kafka Summit, so let's talk about queues and logs a bit. Why do we use queues in applications? There's lots of different things that they give us, right? Like most obvious thing that many might think first of is, I want to decouple the sender and the receiver. They shouldn't be aware of each other, right? Like the fact that this one publishes an event and the other, and then there are 5 different services consuming that. I don't want the producer to know about the consumers. I just want to like conceptually decouple them. And maybe I just want long-term event storage. It's a good use case for Kafka. So these are sort of concerns of, I don't know, just call them composability concerns here. And this is where log really as a semantical concept makes a lot of sense. And then there's all these things like, I just want durability for retries. I want to decouple them like so that they can run asynchronous. As a special case, I'm decoupling the availability of the sender and receiver. If the receiver is down, it doesn't matter to the sender. I want flow control. I want request ordering. Like all those things are more infrastructure concerns. Like the fact that we use queues for this is because it just happens to be a primitive that does that as part of what it does. But it's not really a perfect solution for that concern. It's just like one aspect that you sort of mix in your bigger thing. So I guess the argument would be, instead of dealing with infrastructure for these low-level concerns, use a more high-level thing like Restate. The abstraction level for Restate is built around, I mentioned durable execution, virtual objects, durable promises. By the way, I would love to say durable objects, but that term has been trademarked, so we have to call it virtual objects. It's very much centered around like doing building blocks for compute, state, and communication. So if you've ever actually seen a Flink talk by me, this has been in almost every Flink talk. Like the way Flink has been designed is the core primitive of Flink. The stateful stream transformation is meant to give you sort of a consistent combination of compute, state, and communication. Like these things going tightly together. If they go tightly together, like your logic is your code is in a good place, right? And in streaming, this is like the stateful stream transformation, which is at the sort of the low-level primitive that everything else builds on top of. Here we needed just a little bit more flexible because this space just is more heterogeneous what people do. So it's actually slightly different concerns: durable execution, virtual objects, durable promises, but they all go very tightly together. So it's not like completely different building blocks. For example, virtual objects build on top of durable execution. Okay, so talked a lot about, hey, let's just put something like Restate as a proxy in front of the application, let it persist all the work, the intermediate work. Like, isn't this a gigantic overhead? Like, are we just making everything super slow if we're just like writing to a durable system all the time? I guess we don't necessarily make it super slow. So this is one of the earlier experiments that we did. It's actually an outdated chart. I just noticed this a little too late to replace the chart with a newer one. But even that chart isn't actually terrible. So think of it in the following way. I have a workflow that does 3 operations. like let's say 3 different API calls or whatever. And from the moment I call the service that has those 3 steps, it registers the durable invocation, like creates the first sort of like log around that idempotency key or whatever. Starts executing, first step, puts that into the log, second step, puts it into log, third step, puts it into log, wraps the whole thing up, result back to the user. Every individual step is full consensus, like it really doesn't start the second one before there's full consensus on the first step, synced to disk and everything. And still the entire sort of end-to-end round-trip latency is like on average below 50 milliseconds. So that means if you're actually pulling this in for something, that does 3 operations, you're adding maybe about 50 milliseconds latency to the whole thing, and you win all the nice aspects. So I would say that's probably doable for a lot of applications. Like even on the synchronous, on the hot path, 50 milliseconds is something you can probably stomach. It works in a bunch of languages. I'm using mostly Java here, but there are SDKs also in various programming languages. The model is pretty much, it's not like stream processing where the code runs in the system, but it's separate. It's more like a database and a database client. So the SDKs are actually relatively thin. They run in different processes. That's why they're available in many languages. Restate itself is a pretty unique system in the way it's written. It doesn't build on anything, really. It's a complete bottom-up stack, single binary written in Rust, doesn't need the database or a queue. It's built for 2 things, like number 1, latency, and number 2, ease of operations. Our theory was always, if durable execution should be usable in a widespread manner, it needs to be a lightweight thing that powers it. If you have to come up with like a massive cluster, you probably say, the hassle of actually operating that thing that adds the durability, if that is actually at least as high as the hassle of getting the service right, then you're not going to do it in the end. So it really only works if that thing runs very easy. I have to skip a bit through the architecture slides to reserve some time for a small demo or for some code. But we have a booth here. You can actually come and talk with us all about how it works internally. We just spent a minute on this slide. The internal architecture is a stream processing architecture, which maybe shouldn't come as a surprise, given who's building this. But like everything, every event flows through a durable log, and then there is an event loop that processes this. The log is like a sequence of commands. Think of it as make an invocation, append that journal entry, invoke that external service, update that state, access that state, and so on. So it's basically a log and an event loop. It's extremely tightly integrated. The ability to write to the log, to consume from the log, the leader election between log partitions and the consumers all goes like extremely tightly hand in hand. And this is basically a slice of the system, one partition that works under a stable state in a completely coordination-free way. That's what actually makes it both fast and easy and stable to operate. And it maps actually perfectly to Rust's Tokyo ecosystem for asynchronous coroutines and so on. This is sort of the reason why the system actually goes really well. And then it's a scale-out system, and because we wanted to avoid any cross-partition coordination in the event loops, there's sort of an off-band shuffle component in there that moves events between partitions if actually different invocations attached to different partitions interact with each other. There's a high availability architecture around flexible quorum rights and snapshots to object stores. If you want to go into details there, happy to elaborate that if you come to our booth. Just want to show you maybe one or two quick things on what it actually feels like to use a system like this. Okay, so let's actually first just do the simple-most thing, like an hello world in Restate, and then let's look at a slightly more elaborate thing. I hope you can see this. Is the font big enough, or no? Is there a way to okay, how do I do the presentation mode here? Can I just scroll it like this? Okay. I'll try to fix this. If not, we'll might have to deal with this. Here we go. Okay. Does that do anything? Presentation mode? Oh no, something is stuck here. I don't know. Might have to. Okay, here we go. Sorry for the delay. Okay, so the basic structure of any service is it looks like, we're trying to model this a little bit after what a Spring Boot service would look like. You can also actually embed this in a Spring Boot service. So the simplest way to write this is starting with a service, adding a handler here, an echo handler, and then saying, I'm creating an endpoint here. I'm adding that service to the endpoint. Build and listen. And you can actually say, I'm creating an endpoint here. It basically creates an HTTP2 endpoint. You can also create like a Lambda endpoint or a Cloudflare Worker endpoint or whatever. It's really just the thing that accepts the request and then dispatches the calls. This is the simplest sort of, I guess, restate application. There is, if we want to run this, the restate binary, we have to start this one, and then let's deploy our service. I'm just going to run this locally here. Okay, yeah. Should be seeing this runs on 9080, and then we need to tell restate that, become a proxy for that thing. So it will actually reach out to the service, do like a discovery call and say, what do you actually have? What should I proxy for you? What should I do to add durability to? And here, it says the echo handler. It's actually just do, add an echo here at this handler. We can actually just quickly look at this. You can actually see there's another one already registered, but yeah, there's a few services that restate proxies for. And now we should actually be able to just, just call, and we don't call 9080, which is our service, but okay, yeah. So far, so good. It's not a very complicated service, right? But this is basically the way it works. So you create a service, you register that reset becomes the proxy. Can do all those things. We can try and actually let's say we're starting this in the debugger, putting a breakpoint here just so that this whole thing doesn't actually complete immediately. We could also have put a durable sleep there. Let's actually do that instead. It's actually nicer. Let's just do something like let this sleep for 20 seconds. Duration of seconds 20. Okay. Run this thing here. And if we invoke this now, it's going to take a while. We can use the time to actually ask the system what's going on. Okay, we have an invocation on the echo service here and so on. It's waiting for a while. Let's actually understand what is happening inside that invocation. Okay, it's actually, it's waiting on a durable sleep, a couple of seconds left. So it will actually tell us a lot of what is going on inside. Okay, so far so good. This is not the most interesting example. Let's actually build something slightly more interesting. And let me see if I can start this one. The window has somehow been lost. Okay, give me 1 second. Need to. Oh. Let me bring the IDE back up. Okay, echo service. Don't care about this one. Let's do something slightly more interesting. This example is based on. Has anyone ever been in London and taken the subway? I just came up with the example last week after being there, and I thought it's actually really cool because the way that the subway in London works is you take your credit card, you just like go to the gate, you badge in with your card, and then you go out of the other gate and you batch basically out. So it actually just records, okay, that credit card ID entered, that exited, and then it charges you. And it's actually even more clever than that. It just tracks, I think it charges your first write, your second write. At some point you're hitting a daily max, and then it just like turns this into a daily fare for you instead of a sequence of single writes. I think that actually even works with monthly and weekly tickets. And if you forget to batch out at some point for some reason, at the end at 3 o'clock, it just ends your fare and turns into like a daily write or so. It's actually perfect. Like you never worry about anything. Just like take your credit card or phone or whatever and batch in. And I thought when I was going through this, that's actually a perfect event-driven application. So let's actually build something like this. So it's built, and in this case we're using a restate durable object here. A virtual object, yeah, which basically means we're having a durable execution handler that has an identity and state. The identity of the handler is, let's say, our credit card ID, so we're remembering state per card. And all we're doing is, if we're batching in, we're saying, okay, ongoing journey, we're remembering the station, we're sending a delayed call at 3 a.m. to this function. End of day is a function further below here, you know, and then that's it. And by the time we're batching out, yeah, if we didn't actually batch in, then we're blocking the whole thing because somebody did something funky, but we're clearing the ongoing journey and we're getting the daily fare so far and adding the trip. And if there's still like something that this trip costs because we haven't reached the daily total, then we actually try and charge it. And at the end of the day, if we still have an ongoing journey, we basically just do the same thing. We turn this into a daily trip, try charge, clear the ongoing journey. So this is really all we need to do. And you can actually see there's always a bunch of operations that happen. I'm updating like different states. I'm making call to different APIs, and I'm not really writing anywhere any retries, any concerns about failures. One of the things worth looking at is actually how does, for example, the payment processing work? Because yeah, we don't want to say, you know, if the payment or the authorization didn't work on the first try, we want to immediately just fail, right? So the way we're doing it actually is we're trying, and then we have a delay, some time that we're waiting. This is in our case actually. Let's actually make this a little larger. It's like 1 second. We can make this 60 seconds. It was 60 seconds in a previous version, yeah. So just so that we say, okay, you know, for some reason we didn't get a proper answer when we're calling the payment API to make that payment, and we're doing actually a durable sleep of first a minute, then 2 minutes, then 4 minutes, and we're retrying this a couple of times with like pretty long retry intervals. And we don't have to worry about like any crash happening in the middle or like the sleep being interrupted. All of those things basically are solved for us by the durable execution engine. Okay, let's actually just see how this how this works. I hope I have everything. Okay, I messed the demo thing up here a bit because I did have a Kafka set up here to. Okay, did have a Kafka setup here that was supposed to help me move this to Kafka in a moment, but you know, let's see if we can actually get to this. Let's actually just use a look at the restate case for now. First of all, let's start our restate server again for this one. Okay, we're trying to connect to the broker. That doesn't work because the broker isn't yet up. Okay, broker should actually be up in a moment. Okay. All good. So let's actually try to put some of these writes in. What you can actually see at the bottom, there's like a SQL query. There's a SQL interface in Restate that allows us to just say, you know, give me the state of the internal system, you know, all the state of attached handlers and so on. So everything we're doing here, we can actually just observe this. So the first thing I'll try to do, let me make sure everything is actually still registered, because I just killed things in the middle. Okay, we still have the card record service here. Okay, should be good. So let's actually say we're using we're making a call now to this virtual object. You can see this in the top left corner. We're calling card tracker, and card 31 is just like whatever, my credit card ID. I just wanted something shorter than the long number. And we're saying batch in, and we're saying, OK, at station London Bridge. So we're batching in at London Bridge. OK. Probably haven't started the card tracker service. OK, so on the restate side, we'll actually see that it knows the service should be there. It isn't there. It isn't running, so it's actually doing its retry magic and tries to invoke it. Once it's running, this thing should actually happen. Well, nice demo in that regard, actually. Service was done on the other side. OK, now service is started. Everything should have worked. OK, fine. So we can also see there's like an ongoing journey registered in the state now. Let's actually batch that person out at station bank, and then we've accumulated some daily fare. This is just the state of our virtual objects, right? So the virtual object just implicitly, there's a virtual object now for card 31 that does that. OK, so let's try something else. Let's actually batch in with card number. Which one did we have? I think the 38 is the right one. OK, let's batch in with card 38 at Victoria, and let's batch out with card 38. And this should actually be not so nice, because for some reason, all the cards that end in 38, they take a really long time to go through payment authorization. Like they need a long retry loop. So we kind of have a thing now where we're saying, OK, if we want to make this the synchronous interaction, somebody batching in and out of the subway, they're going to stand there for like many, many seconds until the retry loop that actually does this whole thing working. So it's actually also not how the London subway works. I think how the London subway works is if you actually batch in, there's like a lookup in a cache. Is this like a card we know that's invalid, that is blocked? And if yes, then we don't let you through. If not, then we actually let you through, and we're just running all this stuff asynchronously in the background. And when we want to batch out, and we've seen actually that this fell through, then we're blocking you on batching out, and then you have to go to the counter. So it's actually nice. Let's actually change the code just to do that exact thing. So let me stop this here and just add this little piece here of code, which basically says we're remembering an authorized flag, so we're doing this only once per day. And if we don't see this flag yet, we're running basically authorization, setting the state. If not, we're populating the cache that the card is blocked and return success. One of the interesting things is that thing can actually now still run for a while, that authorization, but it runs in the background. And we also don't have to worry that while we're still batching in and trying to do the authorization, somebody's batching out and corrupting our state machine, because it's a concurrency safe state machine by virtue of running it like as a virtual object on restate. So let's just run it like this and give Gradle a second to recompile it. OK, let's actually try to do this thing again, like number 38, batching in, takes a while. We should see, though, that at some point this puts in the authorization. OK, the SQL query, OK, so we're maintaining this additional field. We have all this now. OK, so maybe that's not really how we want to do stuff in the long run, because this is still too much of a delay. So let's actually say, we just want to move this completely on the asynchronous path. So we can actually do this as well. Let's say we're making the call to this one here, and we're just sending, we're appending the path to send, and then it becomes actually a completely asynchronous operation. It just gives us back an invocation ID and says, OK, I've recorded this durable in my log. Here's like the invocation ID, query about it later, and attach to it later if you want. OK, invocation is already through. It was a little too fast after all. OK, then. So we can actually move this just off the synchronous path. We can actually do the same thing now by just connecting this to Kafka. And I think I need to just get my Kafka set up back, which I don't think we'll have time right now. So let me just show you how this conceptually works. As soon as we have created a handler, we can actually just connect this to Kafka as well by saying, OK, let's create a Kafka subscription that's connected to one of those handlers. This is actually what we would need to do. We have a Kafka cluster here with that's called like my cluster, which it's just basically a mapping to the broker address and port and so on. And then we're saying the topic batch out from that Kafka cluster basically connected to card tracker batch out. And then it will actually map the keys of that Kafka cluster to the keys of the virtual object and the payload there. So every time we're now adding an event to the Kafka topic, we'll actually see this invocation triggered on the restate side. So it's literally just connecting the Kafka events to the durable invocations, and it will do all the offset management for you. Come to our booth and take a look at the demo. We can finish it then. To just conclude the talk and the presentation, there's a few things that I think are worth mentioning here. What we actually built is a durable single writer or transactional state machine with workflows as state transitions. So even like within a state transition with multiple steps, if it tails, we're actually all good. It's stateless code, even though it's stateful logic, but it runs as a stateless code. We don't have partitions, partition tuning, anything. There's no issues with head-of-the-line waiting effects or anything. You can use it very well with Kafka or without, depending on, I would say, what you want. Do you want long-term event storage, or do you just want asynchronous interaction? If you just want asynchronous interaction, go with Restate directly. If you want long-term event storage, go with Kafka. Let's go through these things in... If you want, like, I'm available for questions after the talk. The take-home message for this is, I think there's time to have some better abstraction to build durable transactional applications on Kafka events, and I think durable execution is actually an amazing match for that, especially if you interpret it more in an event-driven way. And I'd love it to see that this is the stack that we'll be looking at in 5 years and think like, oh yeah, did we ever manually write Kafka consumers? Oh God, why did we do this? So that's it. Thank you, and if you want more details, visit either our booth or check out the website. You'll find a lot of examples there. Thank you.